Hi there, welcome to Scientific Adventures of Beardman. Today we're going to look at gravitational potential energy, but because that's the first type of energy, I want to begin by just talking about energy in general. So energy is a concept that was come up with many years ago to understand how, another way I should say, to understand how objects begin moving or stop moving or interact with each other, how macroscopic objects interact with microscopic objects, can transfer motion to molecules and such like that, light, anything that does something can be thought of in terms of an energy, some sort of an energy. Energy is defined as the ability to do work. So the object has to be able to push on something over a distance, and then it's got energy. Okay, so the first kind of energy we're looking at now is potential energy. Potential energy is energy that is stored in something. Okay, usually as a result of its position or its shape. Okay. So you can imagine potential energy stored in a rubber band. You change the shape of the rubber band, it's got energy stored in it. That can then put a force on something as it closes back to its normal shape. Okay, it can do a force over a distance, do work on it. So it's got energy stored because of its shape. We're going to be focusing in particular in this video on gravitational potential energy. Meaning, if we take an object like this teacup, if we lift it higher up, it's got gravitational potential energy because we could tie a little string to it and put it over a pulley and let go, and that could pull that other object up, do a force over a distance. We could imagine it falling on top of something and pushing it down, a force over a distance. Okay, so simply because it's at a higher elevation, it has more energy. Okay, cheers. So first thing you have to do if you want to talk about how much energy it has, you have to start with, what is my frame of reference going to be? Okay, most of the time we'll use the ground as our frame of reference, and we'll say it has a certain amount of energy compared to being on the ground. But keep in mind, even if something is resting on the ground, you could dig a hole out underneath it and it could fall in. It's got energy there. Okay? So you could say like the center of the earth is the absolute zero energy. Okay? But really we just don't worry about it. We just say it's relative to something. We have to pick a frame of reference. Okay? So often, like I said, we'll pick the frame of reference of the ground. So we'll talk about how high you are above the ground. But you could also pick the surface of a table. Okay, set your cup on a table. Okay, you come along and you lift it up. Well, how much energy does it have compared to when it was here? Okay, so it's got a certain amount of potential, gravitational potential energy. So what are the things that are going to affect the gravitational potential energy? Well, one thing is the height. Okay, if we lift it a certain height, if we lift it twice as high, it has twice as much ability to do work. Okay, meaning the height is directly proportional to the gravitational potential energy. Now, I should mention that we're considering ourselves to be in a constant gravitational field as we talk about this, and for anything in a reasonable height that you and I deal with on a daily basis, that's a fine assumption. Of course, the farther you get from the Earth, gravity gradually gets weaker and weaker, and so you could make this much more complicated. But for our purposes, we'll just say it's a constant gravitational field of 9.8 meters per second squared. Okay? So, the height, if I double the height, I have twice as much energy. If I triple the height, I have triple the energy. They're directly proportional. Another thing that would be directly proportional to the amount of energy is the gravitational field. If we're here on Earth, gravitational field of 9.8 meters per second squared, well, that's going to give this a certain amount of ability to do work, a certain amount of energy. If we were on a planet, say Jupiter, okay, or let's go to the moon, okay, if I was on the moon and I went up the same height, well, the gravitational potential energy is significantly less, approximately 1/6 or 1.7 meters per second squared. Okay, so if we drop the object on the, or if we lift the object up on the moon, because the gravitational field there is weaker, it's going to have less energy. You can imagine dropping it, it wouldn't fall nearly as fast on the moon, and therefore it would not have the same ability to do work. Okay, so the gravitational field is directly proportional to the gravitational potential energy. The final thing that will give it more ability to do work is easy to imagine. If you imagine some, let's not use the teacup anymore, some object lifted up, if you're sitting underneath it, you probably don't want this object to do work on you. Okay? What object would you really not want to be above you? Yeah, that's right. Something with a lot of mass, right? Because if it's got a lot of mass, it's going to be able to do a lot of work on you, right? A lot of force over a lot of distance, and that's bad when it lands on you. So you prefer something like a feather to be over you because it doesn't have the ability to do as much work. It has less energy. In other words, mass is also directly proportional to energy. Okay, so if we take all three of those and put those together, we get that the gravitational potential energy of an object is equal to its mass times the gravitational field, which we've called before the acceleration due to gravity, and then multiplied by the height of the object. Remembering that in order to define height, we have to define frame of reference, a point to be 0. Okay? And then we're talking about the amount of extra gravitational potential energy that the object has above that reference point. Thanks for tuning in to Scientific Adventures of Beardman. Keep learning physics. Go out, jump up, get some gravitational potential energy. Enjoy yourself. See you next time.